Can you guys hear me at the back? Thank you. So before I quickly start talking about, before I start a talk, I just want to have a small question. How many of you guys are aware of what machine learning is? Oh, good. That's good. That's good. That's a good audience. And how many of you know what deep learning is? Well, a relatively small crowd. Okay. So that's a good thing. So this particular talk concentrates on a much lower level without showing any code. So yeah, there is no code here. So if you are looking for some code here, you'll be disappointed. So what this talk is about it's about what deep learning is and how it can be used as an effective tool for data analytics. And the second part of the talk is going to talk about another compute problem, a computation problem, which is how to get data into the machines for crunching. Because today, the biggest choke points are databases. Our entire applications are built around databases, right? So databases are definitely the choke points. Now, how to get data as quickly as possible out of the databases into the machines for crunching. So that will be the part of the second talk. Yeah, and please feel free to just interrupt me at any point of time when something is not clear. So without further ado, I'll just introduce what is deep learning. So deep learning is a very effective methodology or a very effective learning tool in order to draw patterns. So till now, like all you guys are already aware of machine learning, it was very easy for a computer to predict, right? It is very easy. You give a linear regression, like Dr. Prithvis in the previous talk mentioned, if you guys were in the same room. So it's very easy for a computer to fit a curve. You give it a multiple points and ask it to fit a circle, ask it to fit a parabola. It can easily do it, and probably it can do much faster than our humans. But let's say there's a very simple and trivial task, like a perceptual task. What are perceptual tasks? If I speak, you're able to understand what I'm speaking, right? And if I show 2 or 3, like you can figure it out what I'm showing. And looking at a person's face, if you have seen him before, of course, you can actually identify that person, right? So things which seem very trivial to humans, those are not trivial for machines. They're not trivial for computers. It's been almost 20, 30 years of research have gone into before we were able to just identify faces. The example in the slide shows. Fine. The problem was, till now till date, machine learning was not successful or was not being mainstream for multiple reasons. 3 most important of them were the research, the availability of data, and the availability of hardware systems, the machines which could crunch that huge amount of data. Fine. So at the current time, with the availability of all 3 things, we are able to come up with deep learning. Fine. So what deep learning is, it's basically an extension of machine learning. How many of you are aware of neural networks? Nice, that's good, that's good. So when you have seen a neural networks diagram, right, at the end of the day, you would have seen probably 3 layers, right? An input layer, and what they call as some hidden layer, which does some crunching, and output layer, which is basically the amount of classes you want to classify. Cars, trucks, motorcycles, etc., or BMWs, whatever, right? But what deep learning is, it's basically a natural extension of neural networks. What it does is it adds more layers into the network. So now one can ask a question, which is, if it was all about just adding more layers, why didn't we do this 30 years before, right? Aren't our researchers smart enough to do that? Well, the answer was they had already done this. Deep learning was proposed in 1998 by a researcher called Yoshua Bengio. And he did this on a very simple data set, handwritten data sets on digits, that's it. But he was not able to extend that onto a bigger systems like detecting cars, detecting objects in a big scene. The reason being the non-availability of computational resources and the non-availability of big data. Now, you would have heard about the thing, right, that if you have more data, machine learning algorithms can perform better, right? But during 1998, there weren't much data available. So that was also partly the reason why deep networks were not as popular as when they were introduced. Fine. So like I mentioned, what happens in case of deep learning is it just adds more layers. It adds more layers to the neural network to create a bigger network which could predict better. Fine. So yeah, let's take a very simple example of how you would do an image classification. How would you use a deep network? So DNN means deep neural networks. How would you use a DNN to do an image classification? By the way, image classification is just an example here. You could also extend this to multiple other perceptual tasks like speech recognition, the text translation from one language to other, and so on and so forth. Right? So how would you do? You will have a data set at the end of it, and the data set would represent images and labels associated with them. Right? So in this case, let's say you've got a bunch of images which are all of cars. You have different varieties of cars, all of them grouped together in a single location. Then you've got a bunch of trucks. You've got a bunch of images of motorcycles, and so on and so forth. Now, that's your input. Now, what would you do? You give that as input to a deep network. Fine. So a deep network, again, like I mentioned, it's a multi-layered neural network. Fine. So you give an image as directly as an input to the neural network. Now, you see a stark differentiation here with respect to the traditional neural networks. What we used to do in traditional neural network was, there was a stage in between. There was a stage in between this images and the neural networks, right? Where some researcher would spend almost 2 or 3 months trying to figure out the images, what kind of features I have to extract out of images, and give those features as input to the neural networks. So that was the step done. What deep learning helps you is, it takes out that, it abstracts out the hand creation or manual creation of features, and it automates that. Fine. So a best example, a best analogy to that is our human brain itself. How do we recognize, let's say, a flower, and how do we differentiate a flower with cars, right? We start, if you think about it that way, you start looking at edges at the end of the day, right? You look at, okay, that's the silhouette of a person, right? And then that's the eyes of a person, nose, and ears and mouth, whatnot, right? And then you combine all of them together to finally say, oh yeah, this person is so and so, right? So you've basically broken down the problem into a simpler set of problems: edge detection, combining of edges into shapes, and combining multiple shapes into whatever object you want to recognize, right? So same thing deep neural networks does also. What they do is, they take the image, the direct image itself as input, they start looking at edges. So if I go back to the previous slide, you see the steps, there are multiple images mentioned there. Those were the parameters learnt by the deep network. So we are not going to go in details about how these are trained. If you want, we could probably have an offline session on that as well. So they detect, so if you look at that way, the first set of layers, they would learn to detect edges. There would be a horizontal edge, a 45-degree edge, minus 45-degree, whatnot. Then it starts recognizing collection of edges, shapes. In this case, eyes, ears, nose, and whatnot. And finally, it will try to see whether the input image belongs to one of the person. That will be a result, right? So it has done a face recognition at the end of that. Fine. So that's what happens in this case as well. It automatically figures out the features for you. You just have to give the direct images as input, and you have to train the network. Now, what do you mean by training? So you give an image as input. Now you have a label for that, right? It's a car. You give a car's image as input, the output is expected to be a car. But instead, if it says a baby, if it outputs a baby as output, then, well, the network is doing something wrong. So the network has an error in it. you propagate back the error, right, from output to the input. Using some advanced calculus operations which we can ignore for the current talk. So basically what it means is that it tries to correct the errors introduced by the network. So you repeat this process for your entire data set. So at the end of the day, what you get is a trained network, the one you see on the right. Now to that network you give an unknown image. You have taken a snapshot of Larry passing by, let's say, and you just give it as an input, right? And then you ask it to predict, and that's your inference stage. Fine. So there are two stages. So the summary of this slide is there are two stages for any deep network. You've got a training phase and you've got an inference phase. During the training phase, what you do is you make the network learn what you want to predict using data set and the labels associated with it, right? So data set could be images of objects. Labels would be what objects they are. Fine. Next, inference would be, sorry, yeah. Okay. Okay. So the question for the audience is deep learning effective enough to identify objects accurately or not, in different angles, colors, in different daylight conditions, so on. So I would defer that question for next couple of slides where I'll show you the accuracy. Fine. So you've got the point. So the summary is you've got two phases, training and inference. Fine. Yeah. Now let's talk about training itself very specifically. What the inputs would be the data set, the labels, and the actual network. You initialize the network with some random weights or the random parameters which will be finally learnt at the end of the training. Next, the input, in this case, it could be, let's say, 100 million training images. Fine. And it could span across multiple categories. There are like plethora of different types of objects available on Earth, right? So for every types of object, you could have a different category. Right? And this simple task, right? It sounds like 100 million training images across 1,000 categories. Well, that itself takes almost 1 week of computation, and that only if you do one pass. As in, you repeat the entire process, right? You go through every image and train it once. That itself takes 1 week of computation on our current CPUs, and you typically need 1,000 such iterations to make your networks work well, to predict well, or to classify well. Fine. So now you get the point. Now you get an idea about how complex and how much compute intensive these tasks could be. Fine. And later on, what do you do? So, yeah. Right. So the question was, is the same thing what Google uses in the Google cars, the self-driving cars? Yes, the answer is yes. So they use something similar, but some more, as in it's much more advanced than this. Mm-hmm. Right. So now the question is, natural question is now, how does the computation happen? And that's what I'm here for. So I'm going to talk about that in, again, a couple of slides later. Yeah. Right. Yes, so the point is, in terms of, logically speaking, it resembles neural networks. That's true, because neural networks and deep networks, they both have a common inspiration, our human brain. How do we think? Neural networks are a simpler version of deep networks. That's all it is. Yeah.
Yeah, so I have a couple of other classification algorithms like SDN, GBM, random forest, and also I have deep learning.
Right.
So do you have any particular scenario where deep learning performance it where like it would be your computer vision or speech recognition or any conventional classification? Is there any particular where deep learning actually perform well compared to other learning areas?
Okay. So the question is, which areas
yes.
Where deep learning shines really brightly, right? To answer that, any perceptual task, I I began the talk by saying the perceptual keyword itself, and I've been throwing the perceptual keyword every time. So any perceptual task where humans are good at, deep networks can also be used there with a reasonable effectiveness. And as for the accuracy, I'll come sooner. Fine. Yeah. Mm-hmm. So the question is it really like a map reduce kind of a question? With reasonable amount of thinking, right? Any problem can be split into map reduce phases, but neural networks are basically a natural extension of how we think. So neural networks are an algorithm. For example, in the previous talk, Dr. Prithvis mentioned about, you were there in the previous talk? Okay, so he talked about a linear regression, right? So linear regression can be thought of as two phases, input and directly the output. Input is X, output is Y. You put a layer in between where you do another stages, so you do two-stage linear regression. That's what a neural network is. You stack such multiple layers on top of each other, what you get are deep networks. Yes, exactly. So as in you filter out, not just filtering. It's like you are splitting the problem into smaller problems which can be solved with reasonable computations. So like I mentioned, right, the example I gave about identifying a face of a person. You first look for the person's head, and you look for his eyes, nose, mouth, ears, and their location. Based on that data, you decide whether this person is A or B or C. You can eventually split into like that, yes. You can try doing that, yes. Yeah. So, like I mentioned, deep networks have been there for past 20 years. And now they have taken a very major chunk of the stage because of three main drivers to them. One, more data. Now because of Internet of Things and whatnot, we are getting more and more data. So the more data you get, the better you can train the networks, right? And second, you've got better models. So on top of that, people have done research over time by building more complex and more bigger networks. Fine. So that will give rise to lesser prediction errors or greater accuracy. And third, the purpose of the talk that I'm here are the GPUs or the accelerators, what they're called as. How many of you are aware of what graphics cards are? What do you guys use graphics cards for? Games, right? So why does a guy from a gaming company come and talks about deep networks? Well, any clue? Any clue? Exactly. It's about the computational power of GPUs. What GPUs are good at? GPUs are good at crunching numbers in parallel. They have got thousands of cores on a single card, by the way. Thousands of small cores. And they can crunch numbers much faster than CPUs, a multi-core CPU. Compared to a multi-core CPU, a many-core GPU can solve problems in a range of order of magnitudes faster. Fine. And that's the third major driver of deep learning today. Like I mentioned, right, the 1 week amount of training for single pass, and you have to do that 1,000 times. That can be done on GPUs within a week's time. So that's where the powerfulness. So that's where researchers or even industrial teams, right? The product teams, they could iterate over their models multiple times and more quickly. Fine. Yeah. Sure.
Brain doesn't act on bytes and digital computing. That's what everybody's talking about neural networks. So it goes through analog computing.
Correct.
Which is totally different from whatever we are doing right now.
Yes.
So is there any research or anything that's going on to build these systems or engines which does analog computing, which makes all these things much more simpler? Because we are going to get taste and smell areas also. Right now we have only visual and audio stuff.
Right. Right. Mhm. Okay, so the question was, what about the future of analog computing in deep networks? So that I cannot answer right now because it's still under active research. People are trying out and people might be trying out. So I don't have any answer for that right now, but hopefully time will answer that. Yeah, sure. So yeah, I think I pretty much answered why. I've pretty much answered, and hopefully I've made clear why GPUs are essential in deep learning. But just again, in case you're not clear, so neural networks, they are inherently parallel. We know in a single layer you can compute operations in parallel because at the end of the day they are all just matrix operations. Fine. And since they are matrix operations, you require a lot of floating point operations to be performed per second. Now let's compare that against GPUs. GPUs, they come from graphics background, so they are inherently parallel. And GPUs, they also come from graphics background where you do matrix operations, so they are good at crunching matrices. And third, flops. Since there are a lot of cores and a lot of ALUs put into the single GPU, it has a lot of floating point. It can do a lot of floating point operations per second. So naturally, GPUs are really good at doing deep networks or doing deep learning. So what GPUs deliver? So which basically means now a model which could take probably a week's time with 1,000 CPUs, you could probably do the same thing in the same amount of time with probably single GPU. So your server footprint reduces. If your server footprint reduces, your cost, maintenance, electricity bill get reduced, right? And best part, all the while, the prediction accuracy of the networks would be the same or better. Fine. So you won't lose on accuracy by just moving to GPUs. And of course, since they can crunch numbers in faster, they could give you the results faster. And yes, 1,000 CPUs work being done by single GPU, so you're definitely going to save some amount of power as well, right? Which will definitely do some cut down on your electricity bill. Yeah. So to give an example, to give an idea about the accuracy, the question which was raised before. So there is this competition called Imagenet. Anybody is aware of this? Oh, nice, cool. But there's only one guy. So Imagenet is a image classification challenge. It's a global challenge. It has 1.2 million images spanning across thousands of categories. So it has different types of dogs, which I don't even understand which kind of dogs they are. So they have such amount of detailed images of objects, persons, whatnot. And they have labels associated with them. What you're supposed to do is you're supposed to come up with a machine learning system, a machine learning code, or let's say a code which learns images and identifies and classifies images. Use that to predict the images in the Imagenet. Now, based on the accuracy of your algorithm or of your system, you will be rated accordingly. Fine. So, just to give you a perspective, till 2011, the error percentage was 26%, which means 75% of the times, close to 70% of the times only they were accurate. So, if you give 4 images, it would classify only 3 of them correctly. Fine. But look at 2012, something nice, something very beautiful happened, which is the error percentage got down by 10%. Fine. And within 2 years, the error percentage got down by almost 10%. Fine. Now, how did that happen? It was during 2012. There is a researcher, Alex Krzyzewski, and his and the team at University of Toronto, who came up with a deep network, and they ported the deep networks onto GPUs to run on 2 GPUs. With those just 2 GPUs and 1.2 million images with 1 month of training, they were able to reduce the error percentage by 10%. Fine. Now, from there onwards, deep learning took off, and then today we are at the stage where the image classification accuracy of deep networks are better than humans. Humans' accuracy was measured around 5.1%, as in error percentage, sorry. Error percentage was 5.1%, now we are at 4.9. Yeah.
Not sure I get your point. So are you trying to suggest
So the question is, what improves accuracy?
No. So you said that because you use, so basically if you use GPUs, things will run faster.
Mm-hmm.
So why should that make it accurate? It's just a question of time.
Yes. Right. Mm-hmm. Okay. So the question is, you're just using GPUs. It means you're crunching numbers in faster. That doesn't mean anything with accuracy. You're right. But let me go back to the slide where I talked about 3 drivers of deep learning, right? You are able to crunch numbers faster because you've got GPUs. It means you can try out various combinations in a given amount of time. Fine. That's one thing. Second, you can now try out bigger and better models at the same time. Previously, let's say if you increase your model size by 2x, it will take 2x more time on CPUs.
I think instead of measuring accuracy as better, just my personal opinion, better measuring is the reduction in time. Because it's like it's not fair. I mean, earlier your model was poorer, and you said it was accuracy X. Now the model is richer. Although you are using GPUs, you can do it much faster. Obviously, a richer model will give you better accuracy.
Right. So the question is, the point is you need accuracy to be, not just accuracy, but time reduction also, right? So there are 2 concepts, right? One, there is something called as strong and weak scaling in computation. What is strong scaling? You've got the same problem size, right, today, and it takes, let's say, X amount of time, X seconds to crunch, to do the simulation. If I increase the problem size by 2x, and if I throw in a GPU, can it run the model within X? You got the point, right? In the same amount of time, I'm doing 2x more work. Can I do that? That is strong scaling. Now, what is weak scaling? Just reduction in time. If I have the same model, throw a GPU in it, how much faster I am? So there are 2 problems. So you have to look at it in both ways. You have to look at it in both ways, that way. In this case, they both go hand in hand. Yeah.
Do you have any open source packages in Python that implement GPU, like that package that we have for our like multi-core processing? Like that?
Okay. So the question is, are there any open source frameworks or softwares available where I could directly use deep learning primitives, right?
No, I can use deep learning in GPU.
In GPUs, yeah. Okay. I'll have to again defer that question for another couple of slides. Okay. But yes, there are frameworks available today. Yeah. So some examples. I'll just show you some very top level examples. These slides they basically talk about what kind of tasks deep networks are good at. So it could do pedestrian detection. It could even detect traffic signs. So you're driving in a car and you've got a camera, and it could do real-time detection of traffic signs, and then it can alert you. Fine. And it can even do image classification, which I've already seen. Not just that, not only images, it can also work on other perceptual tasks like natural language processing. I throw in a paragraph of English text at a deep network. It can tell you what is the sentiment of the person, what would be the gender of the person, what is it trying to imply. It can do such kind of things as well. Fine. And of course, speech recognition as well. Now, some of the examples I can give you are, so Microsoft has this real-time speech translation in Skype. So if someone from China talks in Chinese and then you are speaking in Hindi, it can real-time translate them to of course, vice versa. It can do the vice versa translation. Fine. And Google, of course, uses deep networks in the self-driving cars. And how many of you are aware of Google Photos, where it could now, you can search over Google Photos by just typing anything, right? You could say, show me all Himalaya photos where I was trekking, so it could just show it out. Right? So those things happen because machines can now understand an image and then put a text onto it. It can label the images, and those are the products of deep networks. Fine. Yeah. So like I mentioned, so some of the big industry players who use deep learning are Netflix for recommendation, Google for self-driving cars, for search analytics and whatnot, and Baidu, which is again like Google of China. They use it for speech and image recognition. So Baidu has got the best speech recognizer currently in the world. And yes, IBM Hadoop can also be used. So the slave nodes which are in the Hadoop, right, they could be GPUs. You could do that as well. So some of the use cases would be, like I mentioned, all perceptual tasks, right? So you're going through a video, and let's say someone asks you, show me all videos where Arnab Goswami is yelling at the other person. It could do it. It could potentially do it. Or probably all of it, right? You're right. So yeah, recommendation engines, recommender systems. It could do even, it's even used in the indexing for search. And yeah, and some of the research teams who are currently focused on deep networks are NYU, Stanford, DARPA, of course, the autonomous agency, CMU, Berkeley, MIT, yeah. So they're all now in the space of deep learning. So now to answer the question about frameworks which are available, which can automatically use GPUs. Fine. So here, so this slide tries to list out some of the common most used frameworks. There are other frameworks as well. So you're free to look at our web page on deep learning. So Caffe, let me just briefly walk you through all of the frameworks. Caffe is the deep learning framework. It's in C, C++. It directly uses our GPUs. Now, Caffe is tailor-made for deep learning algorithms only. Torch, on the other hand, it's somewhat similar to MATLAB or Octave. Anybody, if you're aware of it. So it's a scientific computing framework. It also has a set of primitives for deep learning. Fine. And third is Theano. Theano is an expression compiler. So you write a code, the code gets compiled into a C program and it gets run. So even Theano has support for deep learning, but and Theano is in Python, by the way. Then CUDA Convnet 2. CUDA Convnet 2 is again a deep learning application. It's specifically for deep learning application. This was the framework designed by Alex Krzyzewski. He's kind of, as in his team is kind of the creator of this, and then who won the Imagenet competition. And this is in C, C++, and it uses CUDA. CUDA is the programming framework to use NVIDIA GPUs. And the last but not the least is the Kaldi. Kaldi is a framework for speech. It's a toolkit for speech processing. So it could do speech recognition, it could do speech processing and analysis. Fine. Again, it's in C, C++, and a bunch of shell scripts around it. And there are different, each one of them have different licenses. So based on your license requirements, you will have to probably pick and choose the right one, and based on your requirements. Fine. But let's say if you are not command line guy, you like probably a GUIs or probably a web browser, web applications better. So there is an open source framework by NVIDIA. It's called DIGITS. It stands for Deep Learning GPU Training Systems. So it's a simple web front end. So it's open source. Anybody can download it. You download this. You download the software on your system. Currently, only Linux is supported. Download on the Linux and then start a DIGITS server. You can log in remotely onto the server. You can upload images, or you could even work on. Currently, it's only images are supported. You can have different frameworks. You can have different networks that you can play around with, train them, and then measure the accuracy of your system. So you can do all of them with a couple of clicks. That's it. So it looks something like this. So you define a network. So this particular screenshot shows an AlexNet. AlexNet was one of the first deep networks which was created, which won the Imagenet competition, by the way. And you just give it a training set, the one I mentioned, which has a bunch of images and the labels with them. And you just click train. That's it. It automatically trains. It will plot the validation or even the training error over the number of iterations. Fine. And once it is done, you could upload any image, and then it automatically tries to classify that into the current set of objects. Fine. No, so the limitations of DIGITS are it currently supports only images, and it only supports Caffe as the backend, Caffe library. Fine. But yes, that said, we are working on extending DIGITS to have video analytics, speech, and text. That will come sooner in the next releases, in the next few releases of DIGITS. Yeah. So yeah, this is a framework which people can use if you're not a command line guy. Yeah. So with that, I conclude my talk. So before I, sorry, yeah, please. Correct. Mhm. Okay.
Orders, in which you give the input, different models can emerge, right?
Okay.
So how do you do you have any mechanisms where you have worked in terms of saying, I can work with different kinds of inputs, not just throwing GPUs and doing different sorts of combinations, but a more intelligent kind of this thing. And third, in principle, isn't this just more like a big neural network? Because if I have a sufficiently large number of neurons, I could look at a 3-layer neuron network, kind of emulating a wider kind of network.
Yes. So the first question, the last question, which is why not go for a deeper networks? Why not go for a wider networks, right? Which means that, let's say today we have probably 1,000 neurons, right, in a layer. Why not make it 100 million neurons? So to answer that, do you know the amount of complexity that happens with the matrix multiplication, right? So matrix multiplication, let's say of m by m square matrices, it is order of m cube. Now let's say what happens if m is equal to 1 million? So you can imagine the amount of multiplications which you have to do just for one layer. You have not even come to the output layer yet, right? So computational complexity of having a wider network is limiting us from achieving the accuracy of deep networks. One. So the second question was about, sorry, I forgot.
The bootstrapping for the label.
Oh, sorry, bootstrapping, yeah. So the bootstrapping, so the question is about, like today I've got 100 million images, right? Or let's say Imagenet, 1.2 million images. How can I go and then freaking label every each of the images, right? So for that, there is something called as MTurk or mechanical Turk given by Amazon. So what it basically does is, you pose a problem. You say, given all the images, identify where trucks are available, where BMWs are available. You basically pose a problem to the public. Now, real humans log into the system, they look at the images, they basically mark them out, fine, and they label them. Now, that will be given as input to that could be given as input to your network. And for that, of course, you have to pay. For every image classified by a human, he'll probably get a couple of cents. So that's another way to bootstrap.
So that I understood, but isn't any other research in terms of using other kind of machine learning techniques to bootstrap getting the labels?
So there is one way. It's called as data augmentation, meaning you augment data. Today you've got 1 million images. Let's say that's not enough for you. Fine. Yeah, that sounds scary, but it's not enough. So let's say you want to make it 100 million, meaning 100x bloating of your data. One approach you could try out is you could add noise, right? Or you could add lighting, different lightings. You could add lighting to an object which makes it look like it's in the night, it's in the day, etc., etc. But the object is the same, right? So the labels are the same. So you've done the data augmentation, you've got bigger data set, but same labels. So you could try that also. Yes, so currently Digits needs NVIDIA GPUs to work with, yes. Yeah. Any more questions? Okay, I'll still be around. The next part of the talk talks about how one of the big chokers in the entire pipeline, which is the databases, like I mentioned, right? The database is like the star in the star network. So every application depends on databases. So they get choked very, very quickly, and they can get choked very, very quickly. So this next talk is going to talk about a compute problem. Okay. Databases are also about computation. So it's going to talk about a compute problem, which is how to make our databases faster and get data faster, so that you can crunch on the data faster. Okay. Thanks.
See, it is a compute problem in the sense it's not just, so if you take deep learning, actually, we are talking of tens of terabytes of data coming in if you're looking at the images. Deep learning really took off recently after Google really started collecting such huge amounts of data. But then here's the thing, you need to get that data off the disk through the underlying middleware into the deep learning application. And there's a compute problem there in terms of getting the data out and getting it to the thing. So I'd like to talk about this from the enterprise perspective. We use GPUs to accelerate the enterprise. And while we talk about the enterprise, this is a problem that directly fits into the deep learning because you need to get that amount of data out into your deep learning application. This is an example of a very large architecture of enterprise. And if you look at this, you'll see almost everything depends on that database out there, right? And so that really becomes a choke point. How do you get that data out? And especially as you keep adding applications. And I'll talk about how those applications get added and the implications of that, because you're not going to get rid of your existing applications as you add your analytics, etc. So here's what happens. If I look at the software stack, you have Java, C#, or you might have Python, Ruby on Rails, whatever, running on a web server, and you'll usually use Hibernate if you're using Java to access the database cluster. Now the problem here, and by the way, I'm just going to talk about the problems. I will give some data to give you an idea of the implications of using GPUs in such environments. The problem here is as your applications grow, and you can see you saw the architecture, right? The applications keep growing. What happens is your database grows. Enterprises also pack rats. They don't throw away data. So when you do your analytics, you want the archive data also to run your analytics on because you're looking for trend analysis or you're looking at doing pattern match with data that is stored in the past. The database becomes a choke point, right? And so now you add new applications. So you're adding analytics software to it. The database chokes even further. And maybe you add a search engine to it. Gets even worse, right? That's the kind of problem we're looking at today. Now the thing is, all these new applications are coming up. We have deep learning coming up. We have analytics coming up, which is what is being done today. And how do we get that data fast enough out of the database so that you can do that crunch? So some of the answers today, what do? We optimize for query apps, modify our applications, set up clusters, massive clusters. We look at going to SAP HANA, or HP Vertica is looking at NoSQL solutions, which again requires modification of your applications to account for. And these are all expensive and done in flight. We talk of an appliance that really fits on top of the database, or we also run on the cloud. And we use that to get data out and use GPUs to accelerate it. Okay. I'll talk of another case, a problem that exists today. So the impact of that is in terms of the OpEx and the CapEx. But I'll talk of another problem here. Let's take IoT devices. We know that IoT devices are exploding. I mean, you've heard a lot of this thing, and you have apps producing data. What do? We get that streaming data, look for patterns in that data, right, to make decisions, to do various things. Move that data into clusters, running Hadoop apps, and move it into databases. By the way, you won't be able to do joins in Hadoop. So you will need to take it into a MySQL or a database so that you can do more complex analysis on that data, right? So then you're back again to a database, right? Looking at streaming data, if I look at the problem here, the most common applications used in streaming data are Siddhi and Esper. These are open source software. I'm sure you guys are aware of that. And this is a very well-known graph. As the number of events grow, right, as the amount of data increases, your time goes exponential. And that's a problem that you're going to hit as analytics becomes mainstream, as your number of IoT devices and number of applications that are instrumented go mainstream. The time to process is going to grow, and which is what he's talking of. It'll take weeks to do that kind of processing, because you need that amount of data to be able to look for patterns in that data, right? So, and here is our experience by using GPUs. This is the normal data, this thing that we find with CPUs, and those are milliseconds up there. Using GPUs, we've flattened it out, literally flattened it out. So which means that now you can handle data that is significantly larger. In our experience, we've seen that we can handle databases sizes that start at 100 GB and go into tens of terabytes. What do we bring to the table? We talk of a database boost of between 5 to 26 times. And we know that this 26 times is low. We know that with optimized code, we will be able to do almost 100 times. And most importantly, because we have an underlying appliance, you do not need to modify your code. And you can run it directly on the database after putting in the appliance. Basically, we are looking for POCs. We are an early stage startup. We're looking for POCs. We'd like to talk to you if you are using Java J2E and you are looking at scalability, massive scalability that starts at around 100 to 300 GB and goes up, and you're adding analytics. Questions? And by the way, this is not just deep learning, it is applicable to any application in your enterprise.
Ladies and gentlemen, we are open for the Q&A round. We have another 10 minutes to close this session, so you can put your questions across. Thank you.
Rinka.
So again, so if you look at it that if you put the problem, so if you put the problem in that way, right? So it's at the end of the day a face recognition problem, right?
Yeah.
You have to recognize a person having his face. So the example I started with, one of the first slides, right? So there's already a solution where using the deep networks, you can train the network before with lots of faces of humans, train them and then give them input as your video scenes, right? And video frames rather, frame by frame. And then you can try to detect the face of a person and match it against your database to see whether it matches any one of the person in the database or not.
So we can use the digit.
You can definitely use digits for that. Yes.
So digit, which database they use? Digit, which database they use for digit?
But by the way, the digits does not help you with the inference part. There are two phases, right? There was a training and there was an inference phase.
Correct.
Training is where you train the network, given the set of data, given a data set. Inference is where you give an unknown image, like for example, a footage of a person, right? And try to see whether it's the same person or not. So inference is currently not handled by digits as such. So you have to use one of the frameworks. So because at the end of the day, you'll be deploying this out in the wild, right? So which means you'll have to use some kind of frameworks like the ones I mentioned, Cafe, Theano, Torch, or one of those. So you can you can port the networks. So basically these frameworks are compatible. The network models output by one can be used by the other.
So inference can be possible with this frameworks.
They're used for both, but digits currently works only for training.
Yeah, understand. So I didn't understand if the unknown image, how it will be identified. I mean, if it should be in the train set or even unknown also it will be.
It can be in the unknown. Yes, that's the beauty of neural networks in general, not just deep networks.
The last time you were saying DB size is between 300 GB and 5 terabytes, right? Yeah. Right now, most of the ERPs, our enterprise, our customers, they are already crossing 5 terabytes.
Yeah, so we are talking of performances that are like 30 milliseconds on 5 terabytes. We're talking of a completely different level of performance here. Can handle it today using partitioning, etc. But
Performance,
yeah. if you are looking at high performance, because if you try to run these applications on top of it, can you imagine the impact on your existing applications? So you need to look at some of this. It is a massive problem, yes.
Any more questions? Yeah. Thank you.